Astronomers have developed a new method of using starlight to study the nature of dark matter. Dark matter is a mysterious substance, and understanding it remains one of the biggest questions in science today. But it is an important question to answer because dark matter makes up some 80% of all the mass in the universe, and it plays a crucial role in holding stars together in galaxies. Yet scientists know virtually nothing about it. You see, dark matter is invisible, so it can only be identified by its gravitational interaction with normal or baryonic matter. That's the stuff that makes up the stars, planets, buildings, cars, trees, and people in the world around us. This new research, being reported in the monthly notices of the Royal Astronomical Society, maps the location of dark matter by studying how it affects the light from rogue stars in galaxy clusters. Rogue stars are ones that have been pulled out of their original host galaxies by the gravitational tidal interactions of other galaxies inside huge collections of hundreds to thousands of galaxies, all drawn together by gravity and collectively known as galaxy clusters. The study's lead author, Dr. Maria Montez from the University of New South Wales, says it's possible to sort of indirectly see dark matter by examining the faint glow of starlight that exists in galaxy clusters, known as intracluster light. Intracluster light is made up of stars that do not belong to any one specific galaxy, singled out because they move differently compared to stars in galaxies. Instead, these stars float freely within the cluster. Now, as you travel away from the center of a galaxy towards its outskirts, it becomes increasingly dominated by dark matter, and this is also where you find intracluster light. This faint glow of the stars accurately traces the distribution of dark matter, and so may be able to help astronomers explore the very nature of this mysterious element of the universe. Montez's study is the first to confirm the potential of intracluster light in mapping dark matter with current imaging data. Previous studies have examined the reach of intracluster light in galaxy clusters, but Montez's study shows intracluster light can indicate the actual distribution of dark matter. Montez says intracluster light traces the distribution of mass extremely well, thereby highlighting the dark matter in the galaxy cluster. So this means astronomers now have a luminous tracer of this dark matter and how it's distributed in clusters of galaxies. Montez used publicly available deep imaging data from the Hubble Frontier Fields Initiative, an ambitious plan to test the limits of the Hubble Space Telescope by pointing it towards deep space to take images of galaxy clusters billions upon billions of light years away. The result of this initiative has been some of the most amazing images of the universe. The 6 galaxy clusters Montez studied are among the most distant objects ever photographed by Hubble. Until now, dark matter analysis has been achieved through study of a phenomenon called gravitational lensing. First postulated by Albert Einstein, gravitational lensing works by bending or lensing light. A cluster of galaxies can act as a lens, bending light from more distant galaxies. And by studying this stretching of light, it's possible to map dark matter in a galaxy cluster. However, this analytical process is hard to measure, and observing the intracluster light is easier. To test the idea, Montez and colleagues mapped the distribution of intracluster light and then compared it with the distribution of mass in the cluster. With this new method, exploring the distribution of dark matter in galaxy clusters in detail can be done with just deep imaging observations, thereby bypassing gravitational lensing. Now, it won't replace gravitational lensing, but it can be used as an additional valuable technique to help refine existing mass maps. It means astronomers can now see how dark matter is being distributed and then compare this distribution with the results from supercomputer cosmological simulations. The authors are now focusing on additional clusters to see if the match between dark matter and intracluster light holds up. Montez says it can help the gravitational lensing community upgrade their mass maps, and consequently, it will help science understand the nature of dark matter.
Basically, for a long time, I've been studying this very diffuse light. It's called intracluster light. So this light comes from, it's a product of the interactions between galaxies in the cluster. Because of these interactions, individual stars are stripped from their host galaxies, from the galaxies they live in, and end up floating freely in the cluster.
By looking at these free-floating stars, you get an idea of what the dark matter is doing.
Yeah. Exactly. It's what we found in this study. We found that basically studying how this light distributes in the cluster of galaxies, we found that their the distribution of this light is very similar to the distribution of the dark matter in the cluster.
And which clusters did you look at?
So I looked at 6 clusters. That is a survey that made with the Hubble Space Telescope, and the survey is called Frontier Fields. They are the deepest images of clusters ever observed by the Hubble Space Telescope, which for me it's perfect because I study this intracluster light and it's a very, very, very faint light. So yeah, those images were perfect for what I've been doing.
And galaxy clusters, these are the largest structures in the universe.
Yeah, the largest structures gravitationally bound.
Does it look like the dark matter halos surrounding the individual galaxies in these clusters, that's all merged together, has it? What are you seeing?
So basically, in galaxy clusters, basically what you see is it's the global dark matter halo.
For the whole cluster?
For the whole cluster, yes. And if you study how, how it distributes, how this distribution, how the substructures of the galaxy cluster, you observe more or less substructure, you can infer the nature of the dark matter. So that means normally studying the distribution of dark matter in clusters of galaxies is done with a gravitational lensing, which means that you see like a background source, that it's basically the galaxy clusters act like lenses to these background galaxies, so you will see these background galaxies brighter, a little bit distorted. So basically, if you understand how the distribution of matter in the cluster you can basically...
You're using the gravitationally lensed light from the background galaxy to infer the structure of the foreground galaxy cluster.
Yeah, basically it's what people have been doing till now, but the thing is that this process is a little bit time-consuming because you need like very deep images to see all these background galaxies, and also you need to know where those galaxies are. You need a spectrum of those background galaxies. So you have to have those two things. But with the work that we've been doing, because we only study, these deep images, we only need deep images to understand how the dark matter is distributed in clusters of galaxies. Because what we've been doing is comparing how this intercluster light compares with the previous maps of mass of those clusters that have been published. Now that we know that, we can basically study more galaxy clusters because our methodology is more efficient, and we can start, seeing if tracing is not perfect, we can infer some properties of the dark matter, or, we can start studying things in a more statistical way.
We know dark matter appears to react with the baryonic matter in our universe only through gravity. Basically what you're doing is confirming that is the situation and that there aren't any differences in the way gravity acts with dark matter compared to normal matter.
So far, no, but we are a little bit limited by the mass maps.
Yep.
Derived by gravitational lensing. So basically what we want to do is extend these studies, confirm this also with simulations. By the way, I know that it's been confirmed, but we are waiting for the article to be published. But basically, like any deviation from this diffuse light to the dark matter will tell us a lot about the nature of this dark matter.
Every little clue, every little idiosyncrasy with dark matter tells us something new about its properties.
Yeah. The thing is that so far we cannot tell anything about dark matter, anything else,
That's Dr. Maria Montez from the University of New South Wales.